All right, greetings everyone. Welcome to now the third part of the video for section 6.4. Continuing on looking at problems where we'll be solving trigonometric equations and looking at some other techniques for doing that. All right, so here we're asked to solve cosecant of pi over 2 theta equals 2 root 3 over 3 for all solutions. Now, much like one of the previous ones we've done in these videos, cosecant is not something that lies on the unit circle, right? We only have sine and cosine values that lie on there. So what does that mean? How can we deal with that here? Well, recall that cosecant of an angle is equal to 1 over sine of that angle, right? So we're going to use that somehow here. And also before we do that, we have that pi over 2 theta on the inside. As I've pointed out before, we have this technique called U substitution we can use there. So off to the right, I'm going to let U equal the stuff inside the parentheses there. So become pi over 2 theta, which means we can now rewrite our problem as cosecant of now U instead of pi over 2 theta, and we'll bring the theta back in a little bit. We'll make this cosecant of U equals 2 root 3 over 3. And then as we are reminded by this equality here, cosecant can be written as 1 over sine of U equals 2 root 3 over 3. And now we're getting really close to being able to solve this or start to work with this because we have a sine now. But notice it's in the denominator, which is a problem, right? So how are we going to deal with that? Well, the way we can do that is over here on the left. Instead of having 1 over sine, we'd rather have sine over 1 because that would be something we can work with, right? And it actually turns out mathematically what we could do is just switch these. So instead of writing this as 1 over sine, we could write it as sine over 1, which will just give us sine. And whatever we do to one side of the equal sign, we have to do to the other. So on this side, instead of writing this as 2 root 3 over 3, we could flip it and make it 3 over 2 root 3. Now, this is an aside. If you're wondering why we can do that, well, notice if we have something like this, right? Let's say we have 1 over x equals 1 over 4, and we're trying to solve for x. Well, hopefully you would agree with me that it's hopefully straightforward to see that the value for x here should be 4, right? If 1 over something has to equal 1 over 4, well, that something better be 4. And notice if we just flip both sides of the equal sign, so make this x over 1, and make the right-hand side 4 over 1, well, x over 1 just becomes x, and so we get x equals 4, which is what we thought to begin with, right? So that shows us that just flipping the stuff on both sides of the equal sign is a legal move. And so we now have sine of U equals 3 over 2 root 3, which we don't quite recognize probably as something from the unit circle. But if we rationalize, multiply both the numerator and the denominator by root 3, notice we'll get 3 root 3 on the top. And then 2 times we do root 3 times root 3, that'll give us 3. So we get 3 root 3 over 2 times 3 is 6. And then notice the 3 and the 6 can reduce to become a 2 on the denominator. So we just end up with root 3 over 2. So our problem now becomes sine of U equals root 3 over 2. And this is something we can solve, right? We know where sine is equal to root 3 over 2. So if we think of on our unit circle, what that will tell us then is that U can be So root 3 over 2, so it'd be pi over 3 plus 2 pi k. And then we would also get sine is also positive in the second quadrant, so we'd also have 2 pi over 3 plus 2 pi k as our values for u. Okay. Now, are we done here? No, we are not, right? Because recall that we are not trying to solve for u, we're trying to solve for theta. So we have to go back up to here where we have that u equals pi over 2 times theta. We'll use that here. So I need to erase some stuff. So now instead of using these u equals, we'll have pi over 2 theta equals pi over 3 plus 2 pi k, and then also pi over 2 times theta equals 2 pi over 3 plus 2 pi k. And then just like we've done before, to solve for the value of theta here, we'll divide everything on every side of the equal sign here by pi over 2. Okay, and for the first equation here, pi over 2's cancel. So we'll have theta equals, and then we have two sets of fraction division to do here. So we have pi over 3 divided by pi over 2. Again, repeating our process for dividing two fractions, we'll do pi over 3 times, flip the second fraction, 2 over pi. Notice here the pi's will cancel. So we're just left with 2 over 3. And if we do 2 pi k divided by pi over 2, remember 2 pi k can be written as 2 pi over 1. This would be 2 pi k over 1 times, instead of pi over 2, it'd be 2 over pi. Can cancel out the pi's. Multiply 2 k and 2, and we'll end up with 4k. So end up with 2/3 plus 4k. And then doing similar division with the other one. Let's see, we'll get 4 over 3 plus 4k. Okay, and you guys can check my work on that. All right, so those would be our answers there. So 2 over 3 plus 4k and 4 over 3 plus 4k. And notice here that we didn't end up with any pi's in our answers, so that is also a legal thing. All right, let's look now what happens when we try to solve equations like these without values that are on the unit circle. So here we have sine of t equals 0.4. And we're asked to solve these problems between 0 and 2 pi. So how are we going to find a value for t here where the sine is equal to 0.4? Because again, that is not something that falls on the unit circle. Well, recall that the way that these inputs and outputs work, right? This input here would be an angle on sine, and the output here would be a ratio. In order to find the value for t, we kind of need to swap those roles, right? Do we know any way to do that? Oh, right. So if we change this instead to t equals inverse sine of 0.4, that's going to give us an angle where the sine is equal to 0.4. And how are we going to find that value? Right, we're going to go to our calculator. So I'm going to switch here to my calculator. Okay, and first thing I'm going to work or check, because we're finding answers between 0 and 2 pi, is my mode. So I need to be in radians mode, so I'll go down here and change that to radians. And then I'll do my inverse sine of 0.4. And here we get that is 0.4115. And I'm going to use 4 decimals here, places here, which is pretty common when we're looking at radian answers as decimals. So 0.4115 will be our answer. So I'm going to go back to PowerPoint here. So using our inverse functions, we found that t equals 0.4115. However, notice we're asked to find all answers between 0 and 2 pi. And let's think about where this answer we got was, this 0.4115. Which quadrant would it be in? Well, we know that inverse sine only gives us answers in the first and the fourth quadrant. And since the sine value we plugged in, that 0.4, is positive, that tells us this answer should be in the first quadrant. So we're looking at, say, something right here. But are there other places where sine is positive? Well, the answer is yes, right? Also in the second quadrant. So we also need to find an angle in the second quadrant where the sine is equal to 0.4. And this is where our good friend reference angles come back in, because we know that if the angle's in the second quadrant, it has to have the same sign as 0.4115. Well, it also has to have the same reference angle. And recall that for angles in the first quadrant, the reference angles are actually just themselves. So we know the reference angle for 0.4115 is 0.4115. So that would also be the reference angle for the angle in the second quadrant. And so to find the actual measure there, we know that here on the horizontal axis, this value is pi. We have to go back 0.4115 to find our answer. Let's do pi minus 0.4115. And when we do that in the calculator, I get that the second answer here is 2.7301. Okay, so those would be our two answers, 0.4115 and 2.7301. We should be able to check that if we take the sine of both of those, we should get something around 0.4. Okay. All right, let's do the second one. So here we have cosine of t equals negative 0.8. I'm not going to flip over to the calculator this time, but we do the same thing as before. So we'll do t equals inverse cosine of negative 0.8. And so when I do that in my calculator, I end up with not the correct thing. Sorry. There we go. We end up with 2.4981 as our angle, which let's also think about where that is on the unit circle. So we know that inverse cosine gives us answers in the first and the second quadrants. And since the cosine here is negative, right, the value of the cosine, tells us that this 2.4981 is actually in the second quadrant. And again, since the cosine is negative, our other answer should be where cosine is negative, which is actually in the third quadrant, right? And so how are we going to find that angle now? We again need to bring in the concept of reference angles. So we know that these two angles here will have the same reference angles. So once we find this reference angle, we'll know the one for here, and that can help us find our second angle. Now, because we're in the second quadrant, our reference angle is going to be the angle that 2.4981 makes with pi. And the way we find that is by doing pi minus 2.4981 to find the difference there. So when we do that, I end up with 0.6435. So that'll be our reference angle down below. And how are we going to find the blue angle now? We'll notice that we're 0.6435 radians past pi. So to find our angle in the third quadrant, we'll need to do pi plus 0.6435. And when I do that, I end up with the second angle here being 3.7851. Okay, so those will be our two answers. All right, that's it for now. I would suggest maybe going back through this video a second time, especially the stuff from this slide, because it's really important. And this idea of reference angles and finding reference angles for these angles and radians is something we'll really want to have solid for the rest of this section and the rest of the quarter. All right, thanks for watching.